all possible permutations. So that'll be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Let me do that with my left hand. Oh, wait. No? Okay. Be systematic. TVW. Taking two at a time. TV, TW, V. Permutations, huh? Okay. TV, VT, TW, WT, VW, WV. TV, VT, TW, WT, VW, WV. Get a comma. Wow, my left hand is so slow. I cannot even produce these symbols over here. Okay, so there's going to be smiley face, sunshine, sunshine, smiley face, heart, heart, smiley face, triangle, triangle, smiley face. And then you just do the others. So that would be 2, 4, 6 plus 2, 4 plus 2, which is 12. And for A, B, C, D, all possible permutations, that'd be 4 factorial, which is 24. Now, evaluate each expression for perm 2. I know that it's 4 factorial over 4 minus 2 factorial. That's 24 divided by 2, and that is 12. This here is 5 factorial. Over 5 take 1 factorial. Which is 120. Over 4 factorial, which is 24. That's the answer is 5. Let me just check so far. Okay. 12 and 5. Okay, that's correct. Next. Six factorial. Over 6 take 2 factorial. And 720. Over 24. Which is 6 times 5. Six factorial. Over 0 factorial. Which is 6 factorial over 1. And 6 factorial is 720. That's how many permutations there are of 6 objects. 6 objects on a bookshelf, 720 ways to permute them. Now I'm going to express this a different way. 7 times 6 times 5. So 210. Take off 4. 206. So here's 5. Times 6 factorial. Over 1 factorial. Which is 720 times by 5, which is 3,600. Okay, and to check. No, this one's not right. Okay, what I'm going to do is really relax my right hand. Maybe that'll enable me to write more. So this is 7 times 6 times 5 times 4. Two 210, so 840, so 836. Find the number of unique permutations of letters in each word. So no repeats. Six factorial permutations, which is 720. 4 factorial permutations, 24. Now, we have a repeat of the letter E 3 times. So that would be 6 factorial over 3 factorial permutations, which is 720 over 6, which is 120. Am I getting this right? Yep. Here we see 7 factorial, 2 repeats of the R, which is 7 times, which is half of 7 factorial, 5, which is half of 5040, which is 2520. 10 letters, so 10 factorial, 2 repeats of L, 2 repeats of I, 2 repeats of S. So 10 factorial over 8. Now the factorials go 1, 2, 6, 24, 120, 720, 5040, 40,320, 362,880, 3,628,800. And dividing that by 4, we get 907,200. No. And then dividing that by 2, you get 4536,000. Billionaire, that's 11. And I occurs 3 times, L occurs twice. Now 11 factorial, try my best. 39,916,800, and that has to now be divided by 12. So first I'm going to divide it by 2. Fifteen, 195, 1995, and then that, and then divide that by 6. So 3, 3, 2, 6, and 4. Like that. Oh, yay. Correct. Write a word for which there are 30 unique permutations of the letters. Now, to do that, what I should have is a 6-letter word, so that would give me 120 permutations. And then 2 letters which repeat, and another 2 letters which repeat, which would result in a division by 4. No, 5-letter word. Oh, okay, this technically a lot, yeah. Okay, so simplify this. Well, it's x factorial on top, and that on the bottom. So that. And oh no, I'm misreading it. Just try again. Bingo. Half of n factorial. Mm-hmm. Combinations. So this will rely on this formula. And this is 3 choose 2. I mean, really, you can just rely on memorized knowledge of Pascal's triangle. And Pascal's triangle on that row is 1, 3, 3, 1. And therefore, this is just 3. Likewise, this is 4 choose 2. And that row goes 1, 4, 6 for 1, and therefore it goes 6. And this row is 1, 4, 6 for 1 as well. And therefore it's 4. And this is 4 choose 4. And the only way to do that is 1. Yeah, I'm not listing all the permutations, I'm just counting them. So 3, 6, 4, and okay. And there's not a canonical way to list them anyway. So evaluating each expression. So this is (21) times 22, so that's 21 times 11, which is 231. 11 factorial over 8 factorial, 3 factorial, which is 11 times 10 times 9. So 11 times 10 times 3. So 11 times 30. So 330. (12 factorial over 4 factorial, 8 factorial. So 9 times 10 times 11 times 12. 9 times 10 times 11 times 3. 90 times 33. 2970. (25 times 24). That's 25 times 12. And 25 times 12 is 300. And check. 231, 3. I can't believe I got that one wrong. Okay. Right. Destroy all evidence. Why is it not just this? What's going on here? Oh my gosh. Should be 6. That's silly. $12. Let's try it. $45.04. I'm going to give it a go. Okay. This is nuts. I mean, come on. Okay, we can do that. 5 and 3. We can get that one too. Six and 4, going to take them down. 6 and 2, take off the 12 and then reduce that to an 8. I think we can do it. Why not? Eight plus 56. 136 times that by 143. It's not so bad. Okay. 18 choose 11. Really? Oh no, and then all that times by 4. No. All that divided by 7 factorial. Mm-hmm. 11 and 2, strike of 14. 5 and 3, strike of 15. 6 and 4, strike of 12, turn 16 into 8. So it becomes 4 times 18 times 17 times 8 times 13. Eighteen times 17. Is 306. You got 306 times 104. And then quadruple it. So that's actually nice. 31824. 63648. 63648. 127296. How about that? And here, (20 factorial) over 4 factorial. Well, This that turns into 5. That turns into 6. Okay, I'm actually confused by this. Hmm. $95 times 51. So 45, 34, 484, 4845, 4846. Twenty factorial over 15 factorial 5 factorial. So 20 times 19. That would turn into 6. And that would turn into 2. So 19. No. Times 3 times 17 times 2. And 19 by 3. It's 57. That's 34. So 15 and 41. 191. And then 28. So 1938. 19 choose 5. Mm-hmm. Four and the 2. I'm going to turn that into just regular 2. So 19 times 17 times 2. And then take away 6. 19 times 17. Well, that's 323. And then double that. 646. And take off 6. 640. Explain why n choose 2 equals n choose n take 2. I mean, you can do it the formula way. And then n minus 2, which is all goes back to 2. Or you can do it the critical thinking way. The first one is expressing the idea of choosing 2 items from a collection of n individual items. The next one is expressing the idea of not choosing 2 items. Thinking of them as light switches, they're clearly symmetrical situations. And write a combination that equals 1, 2, 3, 4, 5. A combination that equals 1, 2, 3, 4, 5. Just play with this. Nope, that's not true. Hmm. 823. I mean, is that right? Yeah, I think that's right. I'm not sure if that is. 1, 2, 3, 4, 5. Then 823. Yes, that's right. The 823. 3, 7, 11 doesn't work. 17 doesn't work. I do not know. I'm curious if I've gotten any of these right. These are very tough. 2, 3, 1, 165, 495, 300. Okay, those are right. Oh, I got that one right. And that one. And that one. Amazing. But the last one, sadly, not so much. Where did I falter? I really. Oh no! Look! There's a missing factor of 18. Ah. That has to be multiplied by 18. And so does that. So correct it. One 4, 1161, 1162 1164. 11622. Right now. Oh my goodness me. You've got to be kidding me. Of course. Or wow. That's a good one. Mm-hmm. State if each scenario involves a permutation or a combination. Oh, this shouldn't take too long. A team of 8 basketball players needs to choose captain and co-captain. Right, combination. Rob and Mary are planning trips to 9 countries this year. There are 13 countries they would like to visit. They are deciding which countries to skip. Combination. The batting order for 7 players on a 12-person team. Permutation. There are 45 applicants for 3 computer programmer positions. Combination. Okay. How is that permutation? Well, I guess you choose the captain first and then the co-captain second. So that's order sensitive in that manner. I guess I understand. Right. State of each scenario involves a permutation or combination, and find the number of possibilities. Castell and Joe are planning trips to 3 countries this year. There are 7 countries they would like to visit. One trip will be 1 week long, another 2 days, and the other 2 weeks. We'll take a pause here. You will.